Okay, find the determinant by row reduction to echelon form. Oh, these are the lesson activities for section 3.2. Okay, so there were three things that can change the determinant of a matrix as you do row operations. So when you add a multiple of another row, that does not change the determinant. And when you interchange two rows, that changes the determinant's sign. And then if one row of a matrix is multiplied by k, that changes the determinant of the matrix by a factor of k also. So I'm going to do some row operations on this matrix, and I'm going to keep those things in mind, that those are the things that can change the value of the determinant. So I'm going to use equals because these vertical lines without the little tops and feets, right, like without this and this, it means determinant. So I can write equals instead of that little squiggly row equivalent to. So I'm going to say this is equal to the determinant. I can say it's equal because the row operations I'm going to do are row 3 is going to become row 3 plus row 1. That'll knock out the -1 in row 3, column 1. And then row 4 is going to become row 4 plus -3, row 1. Okay, both of those row operations are row operations that do not change the value of the determinant. So I can write equals the determinant of the new matrix. Okay, so rows 1 and 2 don't change, so I have 1, -1, -3, 0, 0, 1, 5, 4. Okay, row 3 is going to become row 3 plus row 1, so I get 0, 1, 5, 5. And then row 4 is row 4 plus -3, row 1, so I get 0. And then -3 times -1 is 3, plus -1 is 2. And then I have 9 plus -2 is 7, and 0 plus 3 is 3. All right, so now I have column 1 taken care of. I'm going to work on knocking out this spot and this spot underneath the pivot that's in row 2, column 2. Okay, so to get rid of those, I'm going to do row 3 is going to become row 3 plus negative row 2, right? I'm going to use the pivot in row 2 to knock everything out. So row 3 plus negative row 2, or row 3 minus row 2. And then row 4 is going to become row 4 plus -2, row 2. All right, and those are row operations that don't change the value of the determinant. So this is going to be equals the determinant of the new matrix. So first two rows don't change. Okay, row 3 minus row 2. So I'm going to get 0 minus 0 is 0, 1 minus 1 is 0, 5 minus 5 is 0, 5 minus 4 is 1. And then row 4 is going to become row 4 plus -2, row 2. So I get 0, 0. And then 7 plus -10 is -3. And 3 plus -8 is -5. Okay, now I'm going to swap two rows because I would like to have a pivot right here. Right, so to get that, to have a pivot there, I'm going to swap row 3 and row 4. row 3 swaps with row 4. Now this changes the sign of the determinant. So I'm going to write equals the negative of what I'm going to get when I make this swap. And then 0, 0, 0, 1. So this matrix is now in echelon form, and I can calculate its determinant by multiplying along the main diagonal. So this is equal to, don't forget about this negative sign. So I have negative, then multiply the diagonal entries. 1 times negative 3 times 1, and you get 3. So that determinant tells us that the columns of the matrix are, so because that determinant is non-zero, everything in the invertible matrix theorem holds, which means that the columns of the matrix are linearly independent. All right, verify that the determinant of AB is the same thing as the determinant of A times the determinant of B for these two matrices. Don't just use the theorem. That is a theorem, that's true, but I'm going to do all the calculations. Okay, so I have to multiply A times B and calculate its determinant. So AB, that's the determinant of 3, 0, 6, 1 times 2, 0, 5, 4. Okay, so 6. So that's first row times first column. And then 0. And then 12 plus 5 is 17. And then 4. Okay, so the determinant of that is AD minus BC. So 24 minus 0 is 24. Also, that's a triangular matrix, so you can just multiply the diagonal entries and you get 24. All right, and then the determinant of A times the determinant of B. So the determinant of A, AD minus BC, is 3 times 1 minus 0 times 6, so that's 3. And the determinant of B is 2 times 4 minus 0 times 5, which is 8, which is 24. Same. Now verify that A transpose is equal to that the determinant of A transpose is the same as the determinant of A for this particular matrix. Okay. So the determinant of A is going to be 3 times 1 minus 0 times 6, which is 3. And then the determinant of A transpose, that would be like that. And that would be A times D minus B times C. So 3 times 1 minus 6 times 0, which is still 3. Use the fact that the determinant of AB is determinant of A times determinant of B to compute the determinant of B to the 5th. Okay, so raising B to the 5th, multiplying a 3 by 3 times itself 5 times would be a lot of calculations. But luckily, I can do this faster by saying, well, the determinant of B to the 5th means the determinant of B times B times B times B times B, which is the determinant of B times the determinant of B right? And that's because of this theorem, which is the determinant of b to the fifth power. So I just need to know the determinant of b. So I could do a cofactor expansion, or reduced to echelon form to find the determinant. Okay, I think I'll do a cofactor expansion to figure out the determinant of b. So this is a little aside here. Okay, so the determinant of b, the determinant of 1, 1, 1, 0, 1, 2, 1, 2, 1. All right, so I'm going to do a cofactor expansion across the top row because it's got a 0 and the coefficients will be 1s. That makes it pretty simple. So it's the first row, so you start with this, you don't change the sign on the first coefficient. So this is going to be a 1 times the determinant of the 2 by 2 you get when you knock out the row and column of that 1. So you're going to get 1, 2, 2, 1. And then I have minus 0 times a 2 by 2, that doesn't matter, plus 1 times 1, 1, 1, 2, knocking out the row and column that 1 is in. All right, so this is going to be 1 times 1 minus 2 times 2 is 1 minus 4 is negative 3, plus 1 times 2 minus 1 times 1. So 2 minus 1 is 1, so I get negative 2. That's the determinant of b. So then I can go back up here and say this is equal to negative 2 to the fifth, which is negative 32. Okay, use that theorem again and the fact that A times A inverse equals the identity to find a formula for the determinant of A inverse. Okay, so let's see. I know A inverse equals the identity. I'm going to take the determinant of both sides of this. So the determinant of A inverse should equal the determinant of the identity. And then we can calculate the determinant of the identity, right? The identity is always just 1s on the diagonals with 0s everywhere else, which means its determinant is going to be 1 times 1 times 1. You just multiply the diagonals because it's a triangular matrix, and you're going to get 1. So the right-hand side becomes a 1 here. And then I'm going to use this theorem to rewrite the determinant of A times A inverse as the determinant of A times the determinant of A inverse. And this is what I'd like a formula for. Now, normally when we're dealing with matrices, you do not divide both sides by a matrix, but the determinant of a matrix is just a number. The determinant of a matrix is a real number. So I can divide both sides here by the determinant of A. And I know that I can because if I know that A has an inverse, I know that A is invertible, which means that its determinant is not 0. So this is only possible because A is invertible. So my determinant of A is cancel, and I get the determinant of A inverse is 1 over the determinant of A. Let A and B be 4 by 4 matrices. The determinant of A is -1 and B is 2. Use known properties to compute the determinant of A times B. Well, that should be determinant of A times determinant of B. I know both of those. -1 times 2 is -2. The determinant of B to the fifth. Well, that's the determinant of B times the determinant of B which is the determinant of B to the fifth, which is 2 to the fifth, 32. The determinant of 2A. Okay, so if you multiply a row of a matrix by a scalar, that changes the determinant by that same scale factor. But if you multiply an entire matrix by a scalar, that means you have to multiply every single entry or every single row by that scalar. So you are actually multiplying all 4 rows of A by the scalar 2. So the determinant is going to change by the factor of 2 4 times every time you scale a row. So this is going to be 2 to the 4th times the determinant of A. You have to scale every single row by a factor of 2. And there are 4 rows because it's a 4 by 4 matrix. So you scale the determinant of A 4 times. So this becomes 16 times -1, -16. The determinant of A transpose times A. Well, this is going to be the determinant of A transpose times the determinant of A. And the determinant of A and the determinant of A transpose are the same. We looked at that in an earlier problem. So this is the determinant of A times the determinant of A, which is -1 times -1, or 1. The determinant of B inverse AB. So this is the determinant of B inverse times the determinant of A times the determinant of B. And we have a formula for B inverse. It's the determinant of B inverse is 1 over the determinant of B. And then these determinants of B cancel, and the determinant of A is just -1.